You're listening to the Common Descent Podcast.
Hello, Will.
Hello, David.
Hello, everybody, and welcome to the Common Descent Podcast, where we talk about paleontology, evolution, Earth history, and so on. This episode, we're focusing on a very specific event in Earth history, the Messinian Salinity Crisis.
This is an event I know practically nothing about.
This is we got a few requests for this one. It's a very famous, it's a niche famous event in Earth history.
Yeah.
The Messinian Salinity Crisis happened about 6 million years ago, and it's when the Mediterranean Sea dried out.
Oh, that's bad.
So we will talk about what that means, why it happened, how it happened, and what the effects were, and also how we know that that happened. Spoiler alert, the answer is so much salt.
Yes.
Just so much salt in the rocks.
Well, it's from the title, you know that this either means too much salt or not enough salt.
Yes.
This is a too much.
A salinity crisis, and the crisis was too much salt. Too much salt and not enough ocean. That was really the issue.
There's your problem.
Every episode of the podcast is requested by our audience. This topic was requested by Jackie, Ivana, Mathrove, and Eric. Thank you all very much for the excuse to do this deep. Well, it's not as deep a dive as usual, I suppose.
This is the shallow end now.
It's gonna be pun central. We've got a whole lot of it. Hey, before we get into the main episode, just a few announcements. We're gonna keep it quick. We've been announcements heavy recently. Number one, we have a Patreon. This podcast is supported top to bottom. Everything that we are able to do, including parts of our own incomes these days, is thanks to our supporters on Patreon. There are all sorts of cool goodies that you can get access to if you are a patron, including live streams with us, director's notes, bonus episode content. We've got bonus noise, which is bonus news and after chat, coming up in the middle of this month. Special merch, patron questions that you can ask for us to answer at the end of the episode, and at a certain level, we will shout your name out on the podcast. This episode, we would like to welcome new patrons Maya and Alir.
Welcome. Thank you so much for joining us.
Thank you very much. Hey, speaking of interacting with us, the end of the year is coming up, and that means the end of the year Q&A.
Woo!
The Q&A submission form is open throughout all of November. When this episode comes out, it will have already been open for a while. You can find the link to that in the episode description on our website, on our social media. Go there, submit your question, one question per person, please. We will have a giant list of questions, and then we will spend some number of hours answering them in an episode we will release at the end of the year.
Yeah.
Also, the end of the year coming up means that we are coming up on the end of Spotlight 2024.
Mm-hmm.
By the time this episode has come out, all but one episode will have been released. The last one will come out the first week in December. It has been a ton of fun, so if you haven't checked those out, go listen to them. We talk to a whole bunch of other cool science communicators, and we have tons of fun conversations. You get some insight into the science communication behind the scenes, and you learn about some other awesome psychomers who are doing very cool work in the paleontology realm.
Just a list full of really neat people.
Also, don't forget that you can follow us on social media. You can join our Discord server. We have a physical mailbox. We have a merch store. There are all sorts of ways to engage with the podcast and support us and be part of our Basque and Coil community. Also, speaking of the time of the year that it is, as we are sitting here speaking into these microphones, it is the day before Election Day here in the United States. So this is just a call out to all of everybody who's listening. We hope that you're taking care of yourself and minding your mental health, and we hope that you are doing okay and cared for in these stressful times that we are in.
Absolutely.
With all that said, let's move on to the news. Before we get into the main topic, we always like to start by going over some news from paleontology, evolution, and related sciences. Will, you told me you're excited about your news today.
I am. And it's doubly so because the first one's about crocs.
Sure.
But also, in a roundabout way, about dealing with excess salt.
Oh, hey,
Yeah.
all right, salinity. We're on topic.
Yes.
My newses are not about salinity. So,
I was debating. I'm like, if this were the last one, I would save it for last so we could segue in. But we'll segue into the news.
my last one is a little bit related, actually.
Slightly salty.
No, it's not about salt, but
Okay.
it is about bodies of water.
Okay.
So we're
right.
going to make it happen.
All right.
You go first.
This is news on marine crocs, specifically the anatomy of the sinuses in their skull and what it indicates about how they may have dove or not have dove. This is research by Mark Young et al. In Royal Society Open Science, and the article is a press release by University of Southampton in phys.org.
Find that link in the blog post.
This study was really looking at evolutionary transitions. That was really kind of the thing they were wanting to look at is, when we see major transitions, there's often huge restructuring of the body. One of the classic examples is whales. Going from land animals to sea animals, watching how their limbs shift and reduce and change into flippers, how their tail adapts, how their sinuses and anatomy in the skull change to hear and breathe and move in the water. Tons of important things happen, and it's a great model for studying that kind of evolution. One of the big things that happens are these sinuses. So these spaces in your skull connected to your nostrils are the sinuses. This is where a lot of mucus gets produced, but also our air openings. It's part of our respiratory system. When we dive, and people have probably noticed this, especially if you have anything that's slightly off about your sinuses, if you dive down in a pool, you'll feel pressure.
Yep.
And it'll be kind of on the front of your face, and it's compressing those air pockets.
Yes, because you have air spaces inside your body.
Yes. In whales, these sinuses have been majorly restructured and reshaped to adjust for this, because otherwise they would probably damage themselves diving as deep as some of them do. The bony area of the sinuses, the bone enclosed sections, has reduced in whales, and they have developed extensions of the sinuses and air sacs outside the skull in fleshy portions. This allows them to better regulate the pressure in the head while they're diving. This study was wanting to look at have other groups who made similar transitions developed their sinuses in the same way. The one they looked at were marine crocs.
Episode 168 for marine crocs.
Absolutely.
41 for whales, as it turns out. Also 172 for whales. We've done a lot of episodes.
We haven't done sinuses yet, so you have to wait for that one. The Thalattosuchian crocodilomorphs are a group of croc cousins that became marine. There's two halves of them, the teleosaurids, which were kind of basically just like ocean gharials, long, thin snouts, but still had legs and arms and would probably still have been able to walk or at least pull themselves up onto shore. The Metriorhynchids, the other side, are full-on dolphin crocs.
Basically mosasaurs.
Yep. Flippers, fluked tail, scaleless, smooth bodies, fully adapted to marine life. And much like cetaceans, this is a terrestrial land group that moved back into the water and became very similarly shaped. So they were wondering, did the sinuses go through a similar transition? So they CT scanned the sinuses of 11 different Thalattosuchian crocs, the skulls of 14 modern crocodilian species, and 6 other fossil croc groups. What they found was an interesting combo. The brain case sinuses, the bony part, did indeed decrease, very similar to what we see in cetaceans. Across their evolution, as they become more aquatic, it reduces in kind, reducing in their semi-aquatic phases and then diminishing, then even further when they go fully aquatic, just like we see in cetaceans. This could be in relation to the pressure, but also could be for buoyancy and diving and things like that. What they found that's different, though, is once they became fully aquatic, the snout sinuses, so similar to the ones we were talking about, the specialized outside the skull sinuses of the cetaceans, expanded in a way in the marine crocs that they don't in cetaceans. So both developed outside the skull sinuses, but they developed them differently, and the marine crocs are big. This immediately gave them the implication that would not make them good at diving.
Right, now you've got a big air pocket in your nose.
Exactly. So probably marine crocs were not deep ocean hunters and divers. They were probably shallow water. They may have been open ocean, but surface.
Right. Yeah, they're not doing like what a sperm whale does.
Exactly.
Where you're diving down into the darkness.
What this was most likely for was their salt glands.
That makes sense.
Yes. Whales and dolphins deal with the extra salt in the ocean with heavy-duty kidneys that filter out the excess salt. But reptiles and birds deal with it with salt glands, often in the nose.
Right. This is very famous in birds. A lot of, especially like seabirds, will have those salt glands on the beak or around the face.
Larger and more complex snout sinuses might have helped drain the salt glands in a particular way. They note that birds with nasal salt glands also have sinuses that exit the snout and pass under the eye, so they also have snout sinuses specialized for those salt glands. One of the things that salt gland animals deal with is encrusting. That salt can build up around the opening to the gland, and if it plugs it, they can no longer excrete salt.
Right.
So they have to get rid of it. Birds typically do this by like shaking their heads. Marine iguanas do it by sneezing.
Yes.
Yes. And that's what they think the marine crocs might have been doing.
So these marine crocs would have had their own version of a blowhole.
Yes.
But they come up and go, and just spray salt everywhere.
They note that when birds contract their jaw muscle, it puts pressure on the snout sinuses, like a bellows, as they put it, and helps
And squeezes
the air out. With the way the marine croc skull is shaped, it seems like they would have created a kind of sneeze with the same sort of contraction and probably would have sneezed much like the marine iguanas.
Cool.
So it's very likely that these expanded sinuses were due to the kind of salt gland they had and would have then precluded them from being able to fill all the same lifestyles as whales did.
Yeah, it's very interesting to see cases where the evolution of one essential feature gets in the way of another part of the lifestyle.
Yes.
Like we've talked about with birds, where birds have those powerful back legs, which are so important for so many of the things that birds do. It also makes them heavier, which gets in the way of flying.
Yes.
So you have these crocs with these salt-excreting glands, which are incredibly important, especially if you're a reptile or a bird, but that might mean you can't be a deep diver.
Yes. Yeah. So and we noted this in the marine croc episode that they have unusually large sinuses.
Yeah.
Now we might have an explanation for why they're so weird.
Very cool stuff.
Yeah.
Pretty neat. I've got a news here that is also about an evolutionary transition. Though it is not about crocs, nor indeed even about vertebrates, it is about insects, and specifically giant cicadas.
Nice.
This is research by Chunpeng Xu et al. In Science Advances, and we will link to an article in Live Science by Sierra Boucher. The focus of this study is trying to do something that is very difficult to do, which is assess the flight performance of ancient animals.
Yes.
That is very difficult to do because we're missing we're missing musculature. It is especially difficult to do with insects because insects not only, do we not typically have soft tissues and stuff, insects also often don't preserve particularly well, especially when they are quite small and squishy. This study is examining flight performance over time in a group called giant cicadas. We talked about these in episode 190 when we talked about cicadas. This is a group called Paleontinidae. These are tree-dwelling insects that were widespread during the Mesozoic. Whether or not they are actually cicadas is they seem to be somewhat closely related to cicadas, but not necessarily actually cicadas.
Yes.
But they are called giant cicadas because they look like cicadas and because they're big. That is one of the reasons why they are a good candidate for trying to study their flight performance. The authors point out that they are often well preserved, in part because they're big. Bigger things tend to preserve better. Some of these paleontinids, giant cicadas, have wingspans up to almost 6 inches or 15 centimeters, which is quite good. There are also 80 well-documented species among this group. So they said, this looks like a group that we could actually get some information from because there are a bunch of them and they are preserved quite well. To get this information on how they were flying, they performed geometric morphometrics on the wings and the body. This is a method that we've talked about before, where you basically quantify the shape of anatomical features by putting landmarks all over it and then feeding it into a computer algorithm that can assess how things are different between different examples.
Yes.
They assessed the shape of the wings and bodies across most of the known species of giant cicadas, and then compared them with their other relatives from the Triassic through the Cretaceous, so across the Mesozoic, the evolutionary history of this group, to see, do we see any changes in that time period? And what they found is, based on the shape of the wings and the related shape of the body, the group split into two major subgroups, the early giant cicadas and the later giant cicadas. That in the early ones, the forewings, the front, so they have two pairs of wings, the forewings and hindwings. The hindwings are quite large, and the forewings are elongated and elliptical in their shape.
Okay.
But in the late giant cicadas, the hindwings are quite small, and the forewings are more triangular.
Gotcha.
Which seems to indicate some sort of change in the way that they were flying.
Mm-hmm.
They noted that there is a distinct shift where the early version gives way to the later version that happens around the Jurassic-Cretaceous boundary. Late Jurassic into the early Cretaceous. To determine their flight performance, they calculated the mass of the flight muscles. They looked at wing aspect ratio, which is the shape and proportions of the wing, like the aspect ratio on a picture. And they estimated wing loading, which is a measure that is a relationship between the area of the wing and the body size.
Yes.
They found that from the early giant cicadas to the late ones, there was a roughly 19% increase in estimated flight muscle mass, a 26% increase in the aspect ratio of the wings. The wings are taking up more area, and wing loading experienced a 92% increase. They point out that higher values of these measurements are seen in modern insects that are high-speed flyers.
Yes.
They estimate, they had a fancy equation to estimate that this would lead to a roughly 39% increase in flight speed and increased maneuverability.
Yeah.
They were just faster, better flyers. So around the Jurassic into the Cretaceous, this group shifted into being faster, better flyers.
Yeah.
This is also around the time that birds start to show up.
That's what I was thinking about.
So the authors point out that this shift in their flying ability could be related to the fact that there's a whole bunch of new predators on the scene. Birds, and we don't know very much about pterosaurs. Pterosaurs were already around in the air. We don't know very much about pterosaur hunting habits on insects, but we do know that there are lots of birds that are really good at catching, picking up insects off of trees and the ground and stuff, but also grabbing insects out of the sky.
Yes.
Like, there are a lot of birds, and that is an unusual thing to be able to do, to hunt while flying. Birds and bats are both really good at that today, at least certain birds.
Mm-hmm.
So this rise in early, mostly small body-sized birds might have been a increased pressure on these insects to become better flyers. Because if you're slow and clumsy, like modern cicadas often are, you're going to get eaten.
Yeah. Very cool. It's neat just learning about... I always love learning the mechanics when they talk about, we wanted to look at the biomechanics of this group to see how well they ran, flew, swam, blah, 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 blah. And I'm always interested to hear what are the measurements that mean the different things. Because sometimes it's obvious, where it's like, this one got a bigger tail fin, it was a faster swimmer. All right, yeah, that makes sense. But every now and then it's like, this shape means this.
Yeah, in this case, it sounds like it's mostly really about the relative size and shape and musculature of the wings compared to the rest of the body.
Yeah.
That relationship is the big factor they're using to estimate here.
Well, it's also fun to note that, like, the relationship between the front and back wings changed with the ship. I find it fascinating It's like when you see a car and someone's like, do you know what that part of the car does? It does this cool thing. It feels like that, but with paleo stuff. And this study's very cool in that regard.
Yeah, I do want to point out, because I thought this was interesting, in the Live Science article, they reached out to Michael Habib, who I'm pretty sure we've talked about before, who does pterosaur research and things like that, to comment on the study, who is quoted as saying that the study is very cool, but also cautions against too much interpretation of flight performance. And it sounds like speed wasn't really the thing to take issue with, according to that quote, but maneuverability.
Yes.
The quote says, basically, I'm a little bit cautious about trying to interpret maneuverability, especially since fast things tend not to also be maneuverable.
Yes.
Those are often at odds with each other. So the degree to which we can accurately reconstruct exactly what their flight behavior was is debatable. But at the very least, they seem to have been more powerful, faster flyers, which would have meant, to some level, better in the air.
Yes. And it is also good to note that there are other reasons you might want to be that. A faster flyer would also make you better at migrating.
Yes.
So, like, could have nothing to do with predators. You need to travel farther in a more efficient time. You can't do that if you're traveling a mile a day.
Yes. Well, and it also, that time where they're pointing out birds are rising around this time is also the time of the rise of flowering plants.
Yes.
Which might have meant that the landscape was changing in a way that either there was more competition for feeding on these plants, or their preferred habitats were more spread out.
Yep.
So there could be, it might not be quite as clean as birds showed up, giant cicadas became better flyers.
Absolutely. Like, is there a new seasonality due to the way the plants are acting, so that plants are notably better at certain times in certain areas now that flowers are a thing?
Yep. I also would be curious to know if those differences in the wing shape and musculature would have an effect on things like takeoff.
Yeah.
Like, does that improve your acceleration?
Right.
And is that an important factor?
Well, it's like, I know there are some things that are fine in the air, but not great at takeoff or landing.
Yeah.
So yeah, it'd be interesting. Cool. My next news is also about a giant version of a thing.
Great.
Giant tadpole.
Oh, fun.
A giant fossil tadpole, the oldest tadpole we know of.
Very cool.
This is research by Mariana Chulliver et al. In Nature, and the article is by Sierra Boucher in Live Science. So frogs are famous for their tadpole phase.
Yes. Episode 91 for frogs.
Going through that aquatic tadpole phase, then into a terrestrial, or, at least a legged adult phase. This is extremely famous about them, but the evolution of this is not as well known because the fossil record for tadpoles is not great.
That makes sense.
Yep. They're a very short time period that they're tadpoles very often.
They're also small and squishy.
And they are in water, which is not always good for fossilization.
Yes. They also have less parts.
Yes.
Because they aren't legged, so they're missing some of the pieces that might make good fossils.
And the parts they have are typically cartilage.
Yes.
It hasn't ossified yet.
So tadpoles are just not great fossil candidates.
One of the big reasons there's such a mystery is the oldest tadpole fossils we had went back to the Cretaceous, dating back to somewhere between 145 and 100 million years ago. The earliest frogs we have, make sure I say this right, date back to the early Jurassic with closely related groups and members in the late Triassic. So we've
got like a 50 to 100 million year gap between the first known frogs and the first known tadpoles.
So we're missing all of that data as to how this tadpole phase evolved and when it evolved. There are researchers who have suggested that maybe the earliest frogs did not start as tadpoles, and that's why we don't have tadpole fossils. You were just a frog, you were born as a frog, and then eventually the life phase got split and a metamorphosis was evolved. This study is on a new specimen of a tadpole from the Middle Jurassic of Patagonia, dating to 168 to 161 million years old, and is identified as the tadpole of the stem frog, so early frog, Notobatrachus degustui, and is super exciting for a number of reasons. One, early tadpole.
Yep.
This is going back to some of the earliest frog
Yes.
fossils.
1, fossil tadpole.
Yes.
2, really early fossil
Really
tadpole.
early fossil tadpole. Oldest one we know of, first stem anurin
Cool.
tadpole.
So an early branch of the frog family.
Yes.
An extinct early branch.
Exactly. So first tadpole from the earliest frogs, and first fossil tadpole to be matched to its adult form.
That is cool.
Yes. So a lot of firsts. Also, really good fossil. Exquisitely preserved, imprints of soft tissues. Includes the animal's eyeballs, gills, nerves, and the gill rakes for its filter feeding.
Yeah, so just a whole tadpole.
Just a whole tadpole. It's also big. It's a big tadpole. They described it as in an advanced stage of development, so it was probably close to metamorphosing into a frog.
Mm-hmm.
The vertebrae, the backbones of the tadpole, had begun to ossify, so they were starting to become bony instead of being cartilage, allowing them to look at the features on the vertebrae and match it to the adult form.
Cool.
So that's what let them see.
Yeah. If
who
they had
this
found
is.
a fresh hatchling tadpole, they might not have been able to compare it to the adults.
Might not have had enough adult features to know who it belongs to. The fact that it's big also helped because it's easier to study. It's easier to see. And notably, both the tadpole and adult form of this species are large. Like, it's a big tadpole and a fairly big frog, which is interesting because tadpole gigantism is a thing we know. Like, there are frogs a day with big tadpoles.
Yes, we talked about that somewhere.
Mm-hmm. I think that came up in the cannibalism a little bit.
Yes, that's what it was. That episode 188 was cannibalism. Incidentally, episode 81 was metamorphosis,
Yes,
so
yep.
this has come up before.
This is not an unknown thing, but it is evidently a fairly rare thing. Like, it's not super common for frogs to have giant tadpoles. The tadpole itself, just to give an idea of when we say giant, is about 6 inches long.
As long as the wingspan of a giant cicada.
16 centimeters. As they described it, like a baseball with a 3-inch tail. 7-centimeter tail. So, big, chunky,
Yeah.
like a potato of a tadpole with a little tail.
Throw that tadpole 80, 90
and the
miles
tail
an
would
hour.
have windsocked just so nicely.
Yeah, like a comet.
It'd be like a Nerf ball.
Whistled like those Nerf footballs. Not the first time we have referenced whistling Nerf footballs on this podcast.
Nope. Is that even a thing anymore?
Because we grew up in the 90s.
Is that even a thing? Do they even make those anymore? Do footballs with tails even whistle these days?
Or have they gotten nerfed?
The adult is just as big, which they said was surprising to them because that's not common, that you get
often
big adult and big juvenile.
The tadpole will shrink
Yes.
into the adult.
So the fact that both are big is typically rare. This goes through a whole bunch of things. It means gigantism in tadpoles is an early thing in frog evolution. That's cool. This duo of big larva, big adult, which is a rare thing, also showed up early on. So that's been around for a while. It suggests that probably wherever they were living was a thriving environment, able to sustain big tadpoles and big adults.
Mm-hmm.
Probably.
You had all those slow-flying giant cicadas
Just
around.
They said it likely had a longer development period, so it was probably took longer to metamorphose for such a size. Other than the size, the body is pretty normal tadpole, so it's not super weird in any other way. So much so that the imprints of the gill rakes are basically the same kind of system that today's tadpoles use to filter feed.
Oh, cool.
Algae and particulate from the water. So it seems to be, it was feeding like a modern tadpole. The way both the abstract and the article made it sound was, it just looks the same.
Yeah, that not only does this imply that frogs have been doing the tadpole thing for 160 million years at least, but that tadpoles have been basically acting like tadpoles since then.
So this is a very exciting study. It puts that debate to rest of, nope, frogs did not start, at least not they did not go a long time without having tadpoles.
Yes.
They had tadpoles pretty much from the beginning. And that seemingly, we don't know exactly what the metamorphose looked like, and there's a lot of questions that still could be answered, but it seems that this really unique and complex lifestyle and life cycle that frogs go through has basically been around since the very early days, seemingly as it is now.
Yeah.
Which is just a very intriguing thing for such a unique system in a life form.
Very cool discovery. Let's do one more news. I've got one about bats drowning in the messel pit.
Whoops.
This is research by Krister Smith, Renata Robinstein, and Joy O'Keefe in Paleobiodiversity and Paleoenvironments. We will link in the blog post to a press release in phys.org via the Senckenberg Research Institute and Natural History Museum. The Messel Pit, episode 160, is a famous fossil locality in Germany that dates back to the Eocene around 47 million years ago. The Messel Pit is famous for being an exceptional site for well-preserved fossils.
Yeah.
There are tons of fossils of all sorts of different animals preserved in the Messel Pit, including some really cool snakes and lizards, things that don't often get preserved very well. The Messel Pit is famous in part for how common birds and bats are preserved in those sediments. Birds and bats are often not preserved very well, especially bats.
Yep.
The Messel Pit also came up in episode 59 about bats because this is around the time of the earliest known bat fossils. So a fossil site from the early history of bats with exceptional bat fossils gets all the attention.
Yep.
Over 500 bat fossils have been discovered from the Messel Pit, and around 70% of them are complete skeletons.
Okay.
Or nearly complete. So, incredible depositional environment. The Messel Pit is known to have been an ancient lake with deep anoxic waters. So the deepest part of the lake was low in oxygen, which contributes to things getting preserved really nicely. But even beyond that, lots of research has addressed the question of was there something special about the Messel Pit that was allowing it to preserve so many well-preserved bats and such.
So yeah, I was gonna make a joke about that one documentary scene of the freshwater crocs grabbing flying foxes as they try to swoop to get water. But if they're complete, then it's not that.
Nope. Definitely not that. So the two major hypotheses for what was going on here, and we talked about this in the Messel Pit episode, have included either toxic gases like Lake Nyos, like was presented in that one episode of Walking with Something or Other,
Yep.
with lake eruptions releasing carbon dioxide or something similar, causing a mass die-off, or algal blooms. That something about the water was contributing to these blooms of algae or cyanobacteria that were toxic to things that would come to take a drink. Both of these hypotheses notably assume an unusually high amount of mortality.
Yes.
Not only were things being preserved here, things were dying here in great numbers. This research seeks to potentially challenge that idea, to ask, how unusual actually are these numbers of what we're finding here? To answer that question, they had to find a comparison in the real world where they could understand how bats get preserved in bodies of water, and they were inspired by anecdotes of bats drowning in swimming pools.
Yep.
They put together an online survey of pool owners asking about things like, what kind of pool do you have? How long is it open during the year? Have you ever had bats drown in your swimming pool? This is a thing that can happen. It's sad because bats are great, but an animal comes in to take a drink, it falls in or something happens and it ends up getting a mouthful of water and then drowning in the pool. And then someone, the owner comes out and has to get the net and scoop it out of the pool. They got around 500 responses from all over the US. Most pools reported no bats, kind of unsurprisingly. Those that did reported an average of 2 bats per year.
Okay.
The range was 1 to 14.
Woo!
I think it was one in Florida somewhere that reported 1 year they had 14 bats drown in the pool.
Ugh.
That was an outlier. The average was 2. So that got them sort of a baseline of like, okay, how often do bats end up drowning in standing pools of water? Then they also did some taphonomic experiments. They got bat carcasses from the Frankfurt Zoo and basically tested, do they sink? And they found that if bats' bodies got filled with water, in their lungs were filled with water, they tended to sink relatively quickly. And if the water was deep, they would settle down to the bottom.
Cool. All right.
Which implies that the process of bats drowning and sinking to the bottom of pools is similar to what we might expect to see in the Messel Pit if they were just normal. If this was just a normal, sometimes bats come over here and they get a lungs full of water and then they drown in the pit.
Yes.
So this is their baseline as, okay, here's what it looks like. They do sink to the bottom, so we could just be getting these fossil bats from regular old drowning.
Yes.
And here are the numbers of how often that happens in pools. So then they looked at the Messel Pit. They looked at the sediment layers in the pit from which they could estimate the years of deposition, what that was referred to in the paper as lake years.
Nice.
Compared with the number of bats that have been found.
Mm-hmm.
Across how many years of lake deposit, how many bats, and they calculated a estimate of between 6 to 9 bats per year in the lake, which is notably within the range of those numbers we got for the swimming pools, and certainly not radically high compared to modern swimming pools. Now, they do point out that there are a lot of differences between a swimming pool and a giant lake that is in the middle of the wild. They point out that pools are obviously smaller than a big lake. They're also closed for part of the year, whereas the lake is open all year round. On the other hand, bats in a natural lake environment are much more likely to be scavenged or eaten before they end up sinking to the bottom. So there are a number of ways that a pool environment is not directly comparable to the lake that the Messel Pit was.
Well, and pools are also more likely to trap because they're smooth-sided, while if you can swim over to a branch in the water or
and
the
crawl yourself out.
Yeah, you can pull yourself out. This is why you get things like lizards and stuff that get trapped in pools as well.
Yep.
Because they can swim perfectly fine, but they cannot get up the, not quite foot of linoleum at the side.
Yes.
Gators and stuff also, like small gators, can also have trouble getting back out of a pool once they've gotten into a pool.
Yep. So there's a lot of differences to consider, but they point out that the pool numbers are fairly comparable to the estimated numbers of what we're seeing in the fossils from the site. They also point out that not every bat that drowns and sinks to the bottom of the lake is going to be fossilized. So our numbers are inexact, but there doesn't seem to be an obvious difference.
Yes.
They point out that according to this swimming pool data, assuming these two things are generally comparable, the Messel Pit might just be collecting a normal amount of bats.
Yes.
And that there might still be a reason why they're preserving so well in that environment, but it might not be that they're dying so often there. It might have been normal background levels of bat mortality that are being preserved extra well.
Yeah. Well, that's similar to what we talk about and interpret at the gray fossil site when people will be like, so what killed all these animals here? Time,
Life.
Yep. Predators, falling, gravity, drowning, sickness, age. Just they died, and they happen to be in a place where if you die and you fall the right direction when you die into the water, this water's real good at turning you into a fossil.
Yes.
And yet that makes it makes sense also with bats to me, because bats are numerous. Like, this isn't if we were finding crazy high levels of pachyderms, elephants, that would be like, all right, something.
Yeah, a herd all fell in at the same time.
You don't just have this many elephants on average. But bats, there's, a single cave can have millions of bats.
Right.
So it makes perfect sense that they could absolutely just be dropping on a fairly regular basis, just because you swooped down to get a drink and you went too low and you splashed into the water. And though, I've seen videos of bats swimming, they can swim. They can't get out of the water from the surface.
Sure.
They have to go to something. And if you fell in the middle of the lake, you might just get exhausted before you get to the edge.
Yep.
So, there's no reason that just naturally, oops, I flew too slow.
Yep.
Now I'm stuck in the middle of the lake.
The big question has always been, was it, because bats don't fossilize well.
Yes.
So the hypothesis is maybe so many bats were dying here that the tiny percentage of bats that fossilize is gigantic.
Yes.
And it's interesting that you brought up the Gray fossil site, because the Gray site is also an example where we don't think there was mass mortality happening. This was just gradual accumulation in an environment that preserved things really well. And we don't have a lot of bats.
Yes, that's a very good point.
Indeed, the first relatively well-preserved bat skull material at Gray was discovered this year.
Yeah.
25 years into the history of the site. So something is interesting about the Messel pit. This paper is suggesting it might not be that the pit was good at killing things.
Yes.
It might have just been extra good at preserving things.
Yeah. Well, and it makes me wonder, like, the surrounding area, because bats are found all over the place, but there are definitely areas with famously dense populations.
Yeah.
Could there have been a cave nearby that was...
Or these trees are just, that's where the bats, on their migratory path or something.
Yes. Was there a mega colony somewhere nearby that it's like, yeah, this lake was not especially good at killing bats, but bats were visiting this lake in the tens of millions.
Incidentally, birds are also extremely common in Messel. Small creatures are very common. So there does at the very least, there is some aspect of good fossilization happening here. But yeah, so to the extent that swimming pools are comparable to a wild lake, it seems that maybe bats were just dying a normal amount at the Messel pit.
Yeah, cool.
It's a very interesting taphonomic study.
Yeah.
The study of how do things end up becoming fossils.
And it's a fun challenge to figure out how do we test this without throwing bats into lakes.
Yes, absolutely.
It's no longer the 70s. We can't do that. That's a cool, clever way to try to get that data.
Yeah, so I'll be interested to see if there's future studies in this direction to sort of strengthen or reject these initial results.
Yeah, do some trail cams around a lake and...
Oh, yeah.
If we do that for a year, would we get data on how many bats?
How many bats show up? Mm-hmm. Interesting. Hey, that's the news. And speaking of dangerous lakes, we're going to take a short break, and then we're going to get to our major topic of discussion, which is that 6 million years ago, the Mediterranean Sea became a place you didn't want to be.
It would be able to kill a lot of bats.
To kill a lot of bats.
It would have been able to kill a lot of bats.
No bats were harmed in the making of this episode, or that study, incidentally. All the taphonomic experiments were all well, I guess they were harmed in the extended making of it. But no people went out and harmed bats.
Bat corpses were harmed.
Bat corpses were certainly manipulated.
Yes. Those bats had already been harmed via secondary
no bats
previous events.
Are harmed in the making of this episode. And indeed, bats will not be mentioned again for the rest of the episode. So bat lovers, you can listen to us after this short break where we will discuss the crisis of salinity in the Mediterranean Sea. About 6 million years ago, the Mediterranean Sea dried up. Mm-hmm. This is one of the most notorious events of the Cenozoic era. This event has a formal name. It is known as the Messinian Salinity Crisis.
Which I did not know that was the term for it.
That's what it's called. Let's break it down. Messinian is a time period. The Messinian is a subdivision of the Miocene epoch. The Messinian age lasts roughly between 7 million years ago and 5 million years ago. It's the last age of the Miocene. It is the time period in which this event takes place. Salinity refers to the amount of salt dissolved in water. That the salinity is a measurement that you could take, for example. And crisis, because it was bad. This was a extremely dramatic event. Let's set the stage. The Mediterranean Sea is a mostly enclosed body of water today. It's essentially an offshoot of the Atlantic Ocean, surrounded on almost all sides by land. Europe is above it, Africa is below, the Levant to the east. Its connection to the Atlantic is a narrow little passage, the Strait of Gibraltar, which is about 14 kilometers wide and about 300 meters deep, which is a fairly small passage. I actually, looking at a map, I was surprised to be reminded how small the connection is between the Mediterranean and the Atlantic.
Like, if you were standing there as a person, it would feel like a large stretch of water. But geologically and landscape-wise, that's not a very wide area.
Yes, it's also noticeably small in comparison to the rest of the Mediterranean Sea. The Mediterranean is part of the ocean. It is a sea in the true sense. It's also quite large. It covers about 2.5 million square kilometers, or almost 1 million square miles, making up about 0.7% of the global ocean surface.
Okay.
Which is pretty big for a single, relatively small sea.
If you're a body of water that can be measured as a percentage of the global, that's notable.
The Mediterranean has an average depth of about 1,500 meters, or 5,000 feet. And its lowest measured depths are about 5,000 meters or 16,000 feet. This is a big chunk of water.
Yeah.
It's also a biodiversity hotspot. There's a lot of unique ecosystems around the Mediterranean. It has its own climate regime named for it, the Mediterranean climate. Also, the Mediterranean is extremely important in human history.
Oh, yeah.
A lot of, or especially early civilizations, but even later civilizations, have been centered around the Mediterranean Sea. So it's a great place for archaeology, as well as paleontology.
Lots of famous history around there.
In the late 1800s, geologists and naturalists reported salt deposits in Italy, near the Mediterranean from the late Miocene epoch. In particular, these were deposits of gypsum, which is calcium sulfate, which, like other salts, can precipitate out of water. This would go on to become a bit of a trend, as over time, scientists found more and more salt deposits around the Mediterranean. Later drilling expeditions found salt deposits underneath the Mediterranean. There is it's a region with all around the same time period, these large salt formations in the geologic record. These included gypsum, halite, which is sodium chloride, that is table salt, salt, and other minerals that are classified as evaporites.
Oh, gotcha.
They're called evaporites because these are minerals that will precipitate out of water as it evaporates.
Yes.
The chemistry here is that you've got your ocean water, for example, that has something, I don't know, it's like 3 or 4% salt content.
Oh, yeah.
Something like that.
I have no clue.
As water evaporates, water is leaving the solution, but the salt isn't. Mm-hmm. So the ratio of salt to water goes up as evaporation happens. Eventually, that ratio becomes so high that the minerals start precipitating out of the water. They can no longer stay in solution.
Yeah, liquids have kind of a load-bearing limit to the amount that they can dissolve. It changes depending on their temperature. That's why mixing like tea and stuff with hot water allows you to super saturate it. But yeah, it's the same way that like rock candy is made. If you make a solution that's super dense and overmixed, eventually that stuff will come out of solution and usually will form like crystals if it's a mineral type structure.
Yes. These are extremely common minerals to find all around the world, but the fact that there were so many deposits of evaporites in and around the Mediterranean gathered attention and spoke to some sort of interesting geological event. Also, investigation of the geology around the coastlines of the Mediterranean eventually showed evidence of down-cutting of rivers.
Oh.
That the level that rivers are at now, in the past, they were lower, leaving this evidence of them carving away at the ground beneath them, which is a thing that happens when sea level drops.
Yeah, because it flows farther down.
Yes, it taking the route to the water gradually carves down at the ground beneath it.
Exactly, yeah.
So as sea level drops, rivers will carve down through the ground because they're heading towards sea level.
I had never thought about that being a side effect of sea level dropping, but it makes complete sense.
Yep. By the 1960s, geologists had determined that something had happened to the Mediterranean at this time. They coined the term Messinian salinity crisis in 1967. This event nowadays has been dated to between 5.97 million years ago until 5.33 million years ago. There's a lot of really fine stratigraphic data in the rocks in that area that have allowed for very precise dating of when this event started and finished.
That's always cool.
These days, we have a much better idea of what happened and the extent of what occurred during the Messinian salinity crisis. Research has led to estimates that the sea level of the Mediterranean dropped up to around 2,000 meters. That is 2 kilometers of sea level drop in the Mediterranean at this time. You'll notice, for those of you that are paying attention, that number is higher than what I said is the average depth today of the Mediterranean Sea.
Whew.
The salt deposits that are preserved in the geologic record there are enormous. There are deposits of gypsum that are hundreds of meters thick.
Whew.
And the halite deposits are around 2 kilometers thick. Like 2,000 meters thick of halite salt deposits.
It's just all the volume of water just turned into the deposit.
Yeah. And in fact, it is, again, for the chemistry people out there, that much halite requires more water evaporation than would have been present in the sea at one time.
Yes.
Which suggests that this happened over a long period of time.
Oh.
In total, there are over 1 million cubic kilometers of salt in these deposits in and under and around the Mediterranean Sea. These sorts of deposits have a name. They are called salt giants.
Salt giants.
From the people who brought you large igneous provinces. Salt giants are these colossal, extensive, very thick deposits of evaporite minerals.
I don't know exactly why my synapses connected this way, but what I immediately pictured were the lava and Ice Titan from Hercules.
There you go.
Except the Ice Titan's salt. So you have large igneous province
just competing
and salt
with each
giant.
other. The Mediterranean salt giants are not the only ones. These are known throughout Earth history, all around the world. So this is a recurring type of deposit, and they tend to form when enclosed seas evaporate.
Mm-hmm.
And that is what seems to have happened to the Mediterranean at this time. At the end of the Miocene, the Mediterranean became closed off from the global ocean, and without that connection, it dried out. So now let's quickly go through the timeline, the phases of the Messinian salinity crisis. Going back way before the salinity crisis, during the early Cenozoic era, the tropical region of the world near Europe, Asia, Africa was home to a body of water called the Tethys Sea.
Yeah.
Episode 171 of this podcast, we talked all about the Tethys Sea, big area of the global world ocean. As continents shifted over time, that sea got split up as different land masses moved into different places. Eventually, the sea split into what we now consider the Indian Ocean, the Mediterranean Sea, and the Paratethys Sea, which for a while was basically the connected basins of the Black Sea, the Caspian Sea, the Aral Sea, and a few other bodies of water up there. It was around 14 million years ago that the Mediterranean lost its connection to the Indian Ocean and became mostly enclosed as we think of it today. Around 8 million years ago, uplift in Europe and Africa began to affect the area where the Mediterranean was connected to the Atlantic. Specifically, this is in southern Spain and northern Morocco, which again, today are only 14 kilometers away from each other, across the Strait of Gibraltar. That narrow path, that sort of pinching of the connection between the two parts of the ocean, began to separate the Mediterranean out. And in the geologic record, we actually start to see fossil and chemical evidence of changing conditions between the Atlantic and the Mediterranean.
Makes
Not
sense.
fully cut off, but closed enough that the temperature, the salinity, things like that start to become different, like they are today. Today,
Yes.
the Mediterranean water is different from the rest of the Atlantic Ocean.
Yeah, because even though they're connected, it's kind of like rooms in a house where you can
Yes.
have a hot room and a cold room because one's facing the sun and one's not. They are sharing air if you have the doors open, but they can't share air instantaneously and even out quickly.
The salinity crisis itself is considered to begin at 5.97 million years ago. This is the time where the first of those gypsum deposits start to show up in the geologic record, that evaporation that is happening. At this time, we also see a shift in the fossil record, where certain plankton vanish from the Mediterranean Sea as conditions in the ocean were starting to change.
So ominous.
It's going to get worse. At this time, for the first phase, the first few 100,000 years or so of this event, we see cycles of evaporite deposition. So you'll get gypsum, and then you'll get a layer of shale or carbonate, which are more typical under the ocean rocks, and then you'll get gypsum again. And there's like 16 or so of these cycles, which seem to be related to changes in sea level.
Yes, absolutely.
Changes in sea level, changes in how much connection there was with the Atlantic Ocean.
Yeah, seafloor being exposed and allowed to dry and then re-flooded and having more normal conditions and then back and forth.
Yes, and it's worth noting that the water doesn't have to completely evaporate
True.
in order for these salts to start depositing. So we're starting to see a early stages of this process. Tectonic activity is uplifting parts of the crust in that area, leading to this limited connection between the Atlantic and the Mediterranean. And then shorter cycles over time in sea level are changing how much water is coming in from the Atlantic. Those shorter cycles are thought to likely be connected to climate cycles.
Yeah.
Like sea level rises and falls with shifting climate, shifting amounts of ice and glaciers and stuff, fluctuating amounts of runoff from nearby land masses. The cycles of gypsum deposition line up with orbital cycles that control climate.
Yes.
So we're seeing this is at a time at the Mediterranean where those fluctuations in sea level were enough to affect how much water is getting into the Mediterranean from the Atlantic, which is very cool to think about.
Well, and it's neat because the geology of the area has set up this notable pinch point so that you're balanced on a much finer point than a lot of other bodies of water might be. So not everyone's going to experience these fluctuations to the same degree, but you are right in this perfect scenario to really be affected.
Yes. Those climate shifts also will affect rivers and streams and stuff, which is where the Mediterranean gets the rest of its water.
Yes.
Is coming in off of Europe and Africa from the nearby land masses. So as that is also fluctuating, you're going to see changes in the amount of water in that ocean. So during this first phase, we have evidence of fluctuating connection between the Mediterranean and the Atlantic, leading to fluctuating water conditions in the Mediterranean, which was started to affect the things that lived in there and started to cause some of that early salt deposition. Phase 2 of the Messinian salinity crisis begins about 5.6 million years ago, or almost 400,000 years later. This is marked in the geologic record by halite deposits. These are the ones that got extraordinarily large. This is thought to be the result of the complete or nearly complete disconnection from the Atlantic Ocean. That where the Strait of Gibraltar is now just became a wall of land that cut off, or mostly cut off, any connection between the Mediterranean and the Atlantic. At this time, it seems the Mediterranean also was disconnected from the Paratethys. So it is just a still very big enclosed sea.
Yeah.
It is at this time that it is estimated the sea level of the Mediterranean dropped around 2 kilometers of sea level drop. This is evidenced in part by, as I said, things like the changing in the course of the rivers. Also, patterns of erosion around the edges of the Mediterranean because now there was a bunch more coastline exposed.
Yep. Crazy.
The reason for this sea level drop at this time is that in, quote, normal conditions, the Mediterranean has a constant source of water coming in from the Atlantic, plus coming in from on land, right, from rivers and stuff. When it gets disconnected, the evaporation rate of that water starts to outpace how much new water is coming in.
Well, it'd be like trying to fill up, an Olympic-sized pool, but with just a garden hose. You might be able to do it, but also on a really hot day, if it might be evaporating almost as quickly as you're putting in, just because the surface area is so massive.
Right. And yeah, the Mediterranean Sea is a huge surface area. So if you get down to a point where all the water it's getting is rivers and rain,
Yeah.
that's not enough to outpace how quickly the water is evaporating. So over the course of hundreds of thousands of years, that sea level slowly comes down. As it does, the water becomes more and more salty. Not because there's more salt in the water, but because the ratio of salt to water is increasing.
Yeah, the water is going down, but the salt that got trapped in there has remained the same
Yes.
the whole time.
Until it starts depositing out.
Yes.
And leaving those salt deposits on the ground, which means that not only was the Mediterranean much lower and drier than it is today, that water was shrinking down into the lowest points of the sea basin. It also means the water that was remaining there was hypersaline.
So salty.
Meaning extra salty. I've seen it described in a number of places as briny.
Yeah.
Similar, this is not unheard of. There are places in the world like this today. Most famously, perhaps, the Dead Sea.
Yep.
The Dead Sea is one of these. The Dead Sea is lower than sea level. It's something like 1,000 feet lower than sea level because it is mostly cut off from other sources of water. It's not connected to the ocean. So what has happened over time is that the water level has slowly evaporated away, leaving the water to be extremely salty. The Dead Sea famously is so salty that you can float in it.
Yes.
The salt content lets you float in it. I know this is true because I've floated in the Dead Sea. Not a great place to have a cut on your hand.
Oh, yeah.
The Dead Sea. That part was not great.
I've heard it described as like you feel like a cork.
Yep.
Where it's because like you can float on the water in a pool, but you have to like lay your body out.
Right.
And
You have to really try.
Control your breathing, or else you'll sink if you exhale. You cannot not float.
Yes. I should specify. It's very hard to sink in the Dead Sea.
Like I bet it would be hard to, like, if you had a pool the same salinity as the Dead Sea, to dive down to the bottom, just because you'd be fighting the buoyancy that the salt is adding to the water.
So during this middle phase of the Messinian salinity crisis, the Mediterranean Sea became much like the Dead Sea. Water evaporated, the sea level dropped down, salt content became very high, and the Mediterranean would have become one or multiple analogs to the Dead Sea. It's possible, and it's suspected that at least at some times, the Mediterranean became multiple separate mini lakes, essentially.
I was wondering.
Because there are multiple low points in the sea floor under the Mediterranean Sea. It's not just all the same deepest point. So as the water level goes down, there is some evidence to suggest that the Mediterranean became several smaller seas that would all have been hyper salty.
Well, and as you mentioned, the amount it's thought to have gone down by is more than the average depth. So there has to have been bunches of exposed area. So it seems likely that some of those could have connected to separate out bodies of water.
That phase, the extraordinarily extra salty phase, lasted about 100,000 years until phase 3 begins at 5.5 million years ago. This is a phase that is called Lago Mare, which means lake sea. This is a time period where we see more gypsum deposits that seem to reflect fluctuating salinity levels.
Okay.
At this time, we start to see in the fossil record of this area fossil organisms that are previously known from the Paratethys. So it seems that some amount of connection formed, again, tectonic shifts in the margins of this area, that allowed the Paratethys Sea, again, the Black Sea, the Caspian Sea and such, to start interacting with the Mediterranean. During this time, the salinity levels of the Mediterranean start to bounce back and forth between what I saw a number of times described as hypersaline to brackish.
Okay.
So,
okay.
hyper salty to hypo salty.
Yes.
Like less salty as more fresh water, less salty water was coming in to the Mediterranean Sea.
Very interesting.
So this is another period of fluctuating conditions in the still relatively dried out Mediterranean Sea. The Messinian salinity crisis comes to an end at 5.33 million years ago, as that tectonic activity that originally closed off the Mediterranean from the Atlantic eventually creates the Strait of Gibraltar, opening a new path that allows the Mediterranean and the Atlantic to connect again. At 5.33 million years ago, we see evidence in the geology and the fossils of the Mediterranean region of a return to marine conditions. We start to see evidence of marine organisms thriving in there as usual, of things like temperature and salt levels becoming what we expect for a marine body of water. Once again, this is a result of the connection between the Mediterranean and the Atlantic, which basically makes the Mediterranean a arm of the Atlantic Ocean again.
Yes.
As it was before.
Absolutely.
This marks the end of the Messinian Age. It's also the end of the Miocene.
All right, right.
And leads into the Pliocene, or the first stage of the Pliocene, which is the Zanclean. The end of the Messinian salinity crisis also has a name. It is called the Zanclean Flood.
Nice.
Because the return of the Atlantic Ocean was seemingly not a slow, gradual, unnoticeable process.
Yes.
We will talk more about that in a little bit. So the Messinian salinity crisis is this really fascinating, we talk a lot about as tectonic movement shifts continental landmasses, continents form and continents break up and islands are formed and such. But also oceans are formed and broken and split up. In this case, the Mediterranean was a broken off piece of the Tethys, and then when it became a broken off piece of the Atlantic, what was left was an enclosed sea surrounded by continent on a relatively shallow portion of the crust, which then led to evaporative processes outpacing the replenishing of this sea, which started with fluctuating conditions in the sea and eventually culminated in a near drying out of the entire Mediterranean Sea.
Yes. And I feel like it's a great example and reminder of we're very familiar with the topography on land of low spots and high spots, but it's often easy to forget that exists underwater as well and is going to affect when sea levels rise or fall or land rises or falls, how that water behaves. And so the complexity of the landscape under the water has a huge effect on how these things happen. And I hadn't thought about the fact of the landmass rising also being a major contributor to narrowing that connection. And then all it took was sea level to go down enough more that now you're too high. You have both moved in opposite directions.
Yes.
And a disconnect was created.
And at the peak of it, the Mediterranean Sea was 2 kilometers below sea level. The surface of the Mediterranean was 2 kilometers below sea level, which had widespread effects on the geology underneath the sea, of the coastline around the sea, And as you might expect, it had enormous effects on the things that lived in the Mediterranean Sea.
Oh, yeah.
After a short break, we will explore the impacts of the Mediterranean Messinian salinity crisis, starting with what the fossils were doing. As I mentioned earlier, today the Mediterranean Sea is a very biodiverse area. There's lots of organisms that live in and around the Mediterranean Sea. There is a high diversity.
Yeah, it's famous.
Especially of things that only live there. The fossil record shows us that during the Miocene, this was also true.
Mm-hmm.
The Mediterranean Miocene fossil record is full of a diverse assemblage of fossils that include planktons, corals, bivalves, gastropods, fish, marine mammals, all sorts of cool organisms that lived in there.
Makes sense.
When the Mediterranean Sea became disconnected from the Atlantic, it had effects on the things that live there. These effects were many and varied. For one thing, the disconnect between the Mediterranean and the Atlantic also disconnected populations. So if you were a population that spread into the Mediterranean, now there's a wall between the two parts of that population. This also restricted the movement of larvae.
Yes.
This is really important in marine environments. A lot of ocean animals disperse by releasing their larvae into the water column to go float away until they find a good place to live.
Yeah, tons of sea animals start their life as plankton.
Yes. This meant with that connection, either permanently or when it was fluctuating, larvae from one side of that barrier could not go to the other side. This also would have cut off migration patterns. Anything like seasonal migrations, anything that was in the habit of moving in and out of the Mediterranean now would have been unable to do that. This also changed the water circulation in the Mediterranean, because when it's connected, the current is based on the fact that ocean water is coming in from the Atlantic. When they got cut off, this would lead to slower vertical circulation. This is something that's really important in the oceans, where you have higher water sinking down to the bottom and lower water rising up. This is an important part, for example, of bringing nutrients up from the depths. It also brings oxygen down to the lower areas.
Because in still water, you would just get everything separating out by layer.
Yes, you get stratification, which is how you get lakes with anoxic conditions, right? Low oxygen conditions deep down at the bottom.
Exactly.
That seems to have happened in the Mediterranean Sea when it got cut off. This would lead to a lack of oxygen at the lower levels, potentially a lack of nutrients at the upper levels, and it would interrupt vertical migration patterns. This is a thing. We talked about this in episode 187, that there are lots of sea organisms that are on a day-night cycle of rising up to the surface and then back down to the depths. A lot of those aren't swimming up and down all on their own. They're riding these currents.
Yes, plankton. There's tons of plankton that are famous for doing this. Plankton are too tiny to swim somewhere.
Yes, that's what plankton means.
Yes.
It's you are just at the whims of the currents.
Like, you will react to stimuli and you may be able to move in certain currents, but you cannot just muscle your way through that much water.
Yes. The drop in sea level over time would have created a loss of habitat. Physically, there is less underwater habitat space now because there's less water. This would have changed connections between the water and the coastline, right? The coast is now way farther along than it used to be. This would have also disconnected deep sea habitats. Because if you're a fish or something that can only live below a certain level in the water, now those lowest points aren't connected anymore.
Yes.
Even if there's still water above, if you can't survive in the top, 500 feet of water, you can't get to the next basin over anymore.
And it could be something where, like, you can't survive those conditions. Or if you're, like, a bottom dweller, like a crab, you now have to walk up into the shallows where you're probably not ready to handle seabirds.
Right.
And things that will happily eat you that you never have to deal with at the bottom.
Or the sharks that live just in the, the photic zone where they get more sunlight.
Yes.
So we're disconnecting both on land and in water habitats. Also, the ocean's getting salty.
Oh, yeah.
That high salinity is going to be inhospitable to a bunch of ocean creatures. Also, the deposits of salt are going to create a sea floor in some places that some animals can't live on.
Yep.
Like if you're a burrowing worm or crustacean or something, you might not be able to live in a salt deposit.
Yes.
That might be the wrong conditions.
Yeah. Salt's such a fascinating thing because it's one of those that's critical. Critical, you need salt.
Yes.
And then if there is too much, it is going to murder you.
Yes. as is true with so many things.
And just, salt always stands out to me because we humans have to worry about eating too much salt. That we have to be reminded that actually if you go survive in the wild, it's going to be the thing you miss the most because it's hard to come by. Mm-hmm. But boy, when there's too much of it, it sterilizes places.
Yep. So the changing conditions of the water, the salt content, also the temperature is going to be affected, both because there's less water, and that's going to change how temperature is distributed, but also the current, the circulation is changing.
Yeah.
Which is going to change how temperature is carried throughout the sea. Oxygen levels are changing. So just the chemistry of the water starts to change. So we've got populations being disconnected. We've got migrations and dispersal being interrupted. We've got deep sea and coastal habitats being fragmented or separated from each other. And the water itself is becoming deadly, or at least less inviting to lots of the things that live there. I found a wonderful paper that summarized a bunch of the changes we see in the fossil record at this time. They note major losses in both phytoplankton and zooplankton, declining numbers in the fossil record of species like gastropods, which are very salt sensitive, famously, snails and stuff like that.
Yup.
They report a almost 50% drop in ostracods, which are seed shrimp. They noted likely due to the loss of coastal habitats. As the coastline is changing, these kinds of animals are losing places to live. And also, deep sea species experience big losses, including things like bivalves, clams and oysters and stuff. Also, bottom-dwelling fish. Those groups decreased dramatically in the fossil record at this time. Well, you're an oceans guy, kinda.
Yeah.
Would you like to hazard a guess which group of organisms the fossil record shows had it the worst during the Messinian salinity crisis? I'll give you a hint. When I say it, you're going to go, oh, of course.
Yep. Coral comes to mind.
100% of coral disappear. Coral, the paper described it, corals vanish from the Mediterranean Sea.
Like, this makes sense for tons of, changing sea level is tough for coral in general because they need a very narrow band of depth of water to be able to get enough light without being damaged and exposed to the surface every low tide, but not so deep that they're not getting enough light to. So they have a very narrow band of shoreline that they can survive. So if the water changes depth either direction, corals can live, but the population has to shift, and they don't do that quickly.
Yep.
So there's always tough. So that, and then also you're changing the chemistry, and they can't move or adjust. No. So and plankton dying off, which is their other source of food. Yep, that makes sense.
Yep, corals vanish.
Ooh, that's bad.
The Messinian salinity crisis was a regional mass extinction. It's not an actual mass extinction because this was located in one spot, but huge numbers of local species, depending on the group you're looking at, these are like 30%, 40%, 60% of the biodiversity in these different groups disappears from the fossil record as the Messinian salinity crisis starts and gets into its peak during the middle. This was a rough time. This was not a time to live in the Mediterranean.
Yes. Well, and this is one of those weird moments where like having to distinguish if this counts as a mass extinction or whatnot. But like this would be like losing a rainforest, or like this is losing a major, huge, not continent scale, but a large, diverse ecosystem. It's notable.
And not only did the disconnect from the Atlantic Ocean create all of these biological dramatic impacts in the Mediterranean Sea, so did the reopening of the connection with the Atlantic Ocean. At the end of the Messinian salinity crisis 5.33 million years ago, the geologic record shows us the return to marine conditions and an influx of fossil things.
Yep.
A whole bunch of organisms now coming in from the Atlantic Ocean. The paper that I was reading noted that the fossil record is actually very different before versus after the salinity crisis.
Not what I would have expected.
Some species seem to disappear or decline in the Mediterranean, but then come back.
Mm-hmm.
And it's thought that these are things that basically survived in the Atlantic.
Yes.
Right? On the other side of the wall, they survived, and then when the connection came back, they just came back in and re-inhabited the Mediterranean.
Yeah.
Some species seem to be endemic to the Mediterranean, things that, as far as we can tell, only lived in the Mediterranean. And some of these do seem to have just toughed it out.
Yeah.
Survived, and then when conditions went back to normal, just came back, right? Repopulated to their former conditions.
I've been here the whole time.
Exactly. Most of them did not do this.
That makes sense.
The paper noted that most of the recovery from the Messinian salinity crisis was not recovery from within. It was recovery from without.
Yeah, it was repopulated, but by Atlantic species.
The paper noted that depending on what group you're looking at, so plankton, fish, mollusks, between 40 to 80% of the species after the salinity crisis weren't there before.
Yeah.
So you had this massive turnover. Corals were a 100% turnover.
Yeah.
Any corals that lived in the Mediterranean after this event were new. They came in because they did not survive by staying in place. So this caused a full turnover. The 2024 study, this was the same paper that I was reading, identified approximately 800 species that were thought to be endemic, so only found in the Mediterranean before the salinity crisis. Fewer than 100 of those make it to the Pliocene after the salinity crisis.
Wow.
So a 80 to 90% extinction rate of endemic species that had nowhere to go, basically.
Well, and all of that makes sense because when you have species that live in one location, that this is often what happens when the situation, the dynamics in that ecosystem change. Is endemic species don't fare well because they don't have backup from outside to repopulate. It's only you. I am surprised by, I just hadn't thought about how many endemic species there would be in the Mediterranean.
Yeah, but it's the Mediterranean.
Yeah. And so I had kind of assumed that there would be a lot more familiar faces repopulating.
Mm-hmm.
But yeah, it makes sense that the loss of that many endemic species made space for a lot of new species to enter the fossil record.
So the Mediterranean from the Pliocene till today is much more Atlantic in its biodiversity than it was beforehand.
Crazy.
Incidentally, and this is just a side note, the paper mentions that after the salinity crisis is when dolphins and great white sharks first appear in the fossil record of the Mediterranean.
Oh.
Which is pretty cool.
Nice.
Those were a couple of the species that came in after the event happened.
The ones who stuck out the crisis.
That's what they had to look
The water starts coming over the ridge, and they're like, oh, thank goodness, and then just teeth.
Sharks, dolphins.
No.
Another interesting side effect of the salinity crisis is the pattern of diversity in the Mediterranean. Researchers have apparently noted for a long time that the Mediterranean Sea is not equally diverse across its whole range. There's a gradient of species richness.
Makes sense.
As you move from west to east, there is lower diversity of species. Research in the past has tried to look for, is there a temperature gradient? Is this related to the salt content, the chemistry of the water? This paper that I've been referring to looked across the fossil record, and they found that that gradient of diversity wasn't there before the salinity crisis.
Oh.
That gradient of biodiversity, more diverse closer to the Atlantic and less diverse farther away from the Atlantic, might be a side effect of the sea being repopulated.
Yeah.
It got repopulated quicker on the west side.
Exactly. Because I would have assumed, just given that information, that it has to do with, like, the flow of things or something. It's like, well, yeah, nutrients is coming in more densely from the ocean.
Sure. And it could be something like that, absolutely.
But that also makes, especially if it seems like it wasn't that case beforehand, when the situation, at least flow-wise, should have been pretty similar to today, that makes a lot, that we're just, it hasn't evened out yet.
Yes. Now, that
weird.
paper does note that their study only looked at the fossil record shortly before and shortly after. It's possible that it did even out and then it shifted again closer to today for some unrelated reason.
Yeah, like, and if we go back further before it, maybe we find that there is a gradient in the past for some other reason. So that might be a fluctuating situation.
So it sounds like, at least from what I read, it sounds like it's not a sure thing that the modern condition of the Mediterranean is directly because of the salinity crisis, but it is an intriguing pattern.
Yeah, that's an important note to double check on, because that's very interesting.
Now, as you might expect, the Messinian salinity crisis did not just have radical effects on marine life, also had impacts on terrestrial life.
Yup.
I have seen a couple of papers that have made note of the dispersal of different groups of animals on land around this time, that there may have been more passages available, more land available to cross over. I want to highlight one specific instance that I thought was really, really cool. The Balearic Islands are an archipelago in the Mediterranean today. They are on the western side. They're near the east coast of the Iberian Peninsula. So they're over there by Spain and Portugal. They are a set of islands. Research into the fossil record of these islands find that new species seem to appear during the Messinian time period. These species that start showing up on the island include things like rabbits, rodents, shrews, relatives of goats. Many of these have close relatives in the fossil record of the mainland nearby. Some of them show island gigantism, including giant hamsters and giant gerbils.
Oh!
Now, I did look, and I did not find like a documentation of how big these were. I assumed that they were still really small.
Yeah, like
because usually that's the case.
when it's one of those where, like, a guinea pig, which is like that's
pretty big.
That's a good loaf of bread almost sized rodent. A guinea pig sized hamster or gerbil would be a giant hamster or gerbil.
Yes, exactly.
But a guinea pig is still very much rodent sized.
So if anybody out there knows how big the giant hamsters of the Balearic Islands were, let us know. I could not find a reference to tell me how big they were. Many of these species that show up on the island during this time period are thought unlikely to have swum the distance, especially given just their habits, the kind of conditions that they can survive. It's thought that they more likely walked.
Yeah.
That the sea level at times dropped so low that goat antelope. They're called goat antelopes, caprines, just the general group.
Yes.
But also shrews and gerbils and stuff were able to just stroll between Spain and these islands off the coast.
Which, like, today there are islands that can happen with like tides.
Yes.
Like, there was one that when I visited Australia, we stayed at a place and there was an island that we walked to at low tide, had to stay there for the day to wait for the next low tide to walk back.
Yep.
But if you're fluctuating the water levels, because there's not going to be tides in this isolated place, because you're not having the flow of the rest of the ocean. So there should not be tidal.
Yeah, or at least certainly not nearly
as dramatic.
Yep.
So if a stretch of land gets exposed for a few years when things are particularly low, allows animals over, and then water comes back enough to cut them off, easy way.
Now you are isolated.
That's very cool.
They did note that there was discussion in one of the papers I read that they were like, it is very unlikely that these animals looked over and saw those islands and then walked over to the islands.
Yes.
They were probably living on what was formerly the seabed.
Yes.
That there would have just been these exposed areas of the Mediterranean basin that were just now land habitats. That animals were... So for those gerbils, the islands weren't islands, they were just mountains. It's like, oh yeah, I'm in the valley between Spain and those mountains over there, and then they went and they lived on the mountains, and then the mountains became islands later when the sea level rose again.
So cool.
So this event had all sorts of dramatic impacts on the animals, probably plants. I didn't find any direct information about the plants. I imagine it also would have had incredible impacts on the plants. Life in and around the Mediterranean was radically adjusted.
Well, and like just from the standpoint of life on land is affected hugely by living near the shore.
Yeah.
Like seabirds that live near the shore are going to hunt in the water. There's famous things of like eating things that wash up on the shore.
Yeah.
So changing what's alive and what the population is looking like in this body of water, that's the largest body of water in this area, is going to have huge effects on any animal that's hunting or feeding off of that stuff.
Well, it also would have meant as the sea level dropped, the distance to the water would have changed.
Yep.
So, like, if your ancestral nesting ground is over on that area, the ocean is getting farther and farther away from where you're supposed to be nesting.
Absolutely.
And if there are animals that would go for a swim, like we think of like otters doing, that you go swimming in the water to grab food and then eat it, well, A, your food might not be there anymore, but even if it is, that water is now way saltier than it was before.
Yep.
You might not be able to survive as long in that water. You also, as we were talking about with the Dead Sea, might not be able to dive in that water very easily.
It might just be more exhausting to have to now move in this more buoyant water. So, it would be huge. I also wonder how much of the exposed areas would be like salt flatty.
Yeah, like the Salt Lake.
Yes, exactly.
In Utah.
There are salt flats on the world today that are dried up areas like what happened here, but stayed dry, and you just have plains of salt where nothing can grow or live because it's just salt.
One time I visited Salt Lake in Utah, and one of the things I remember is that as you walk across the salt flats, there are dead birds just laying here and there, because when a bird dies out here, there's nothing to eat it.
Yep.
There's just no one's out there scavenging. It's dead birds and salt and brine flies.
This is why they do like land speed records out there for like the fastest cars and, rocket cars, because there's nothing to hit because nothing grows out there.
Yeah, there's no roadkill.
There's no roadkill. There's no trees. There's no cacti. So as it pulls back, it also might be a situation of the forest and plants can't follow the shoreline in some areas.
Gypsum.
Because it is this mineralized landscape that is harsh and inhospitable. So it also would be probably taxing for animals to move across that. Like, that's going to get hot.
Yep.
That's going to get, if you're a small animal, that much salt could just be toxic for you to spend that much time. Like, it's bad.
Yeah, this was a rough time. The Messinian salinity crisis lasts about 640,000 years. Right? The first 300,000 or 400,000 are that first fluctuating time period, and there's roughly 100,000 years in the middle where it's peak desiccation of the sea. At 5.33 million years ago, the salinity crisis ends. It ends with the refilling of the Mediterranean. Continuing tectonic activity shifts the Gibraltar Isthmus, which leads to overtopping.
Mm-hmm.
Overtopping is a term that you'll hear. Usually I think it refers to like lakes and stuff, but like dams this can happen to. This is why very recently in this part of the world, when Hurricane Helene came through here, we were worried about dams, because if the water level gets too high, the water will start spilling over the dam, and that flow of water can also damage the wall of the dam.
Yeah, dams aren't built to have water flow on top of them.
Yeah, they're built to hold the water.
They're built very specifically for that.
They're not built to hold back a current.
Yes, and not to be under a current.
Exactly.
Like, structurally, they are meant to do one job.
This overtopping like this is reported to have happened a bunch during the Pleistocene, the Ice Age, where you would have things like lakes. When glaciers would melt, lakes level would rise, and then you would get these floods.
Yes.
Much like how a dam might flood, these overflows, and in some cases that overflow can erode the wall of that lake and lead to an even bigger flood in that area.
Permanently make a bigger opening that wasn't there before.
Yes. That, or something like it, seems to be what happened at the end of the Messinian salinity crisis.
What I'm picturing in my head right now is like when you would play in the pool or at the beach and you have a bucket and you slowly push it out in the water and you're like resisting the buoyancy of the bucket, but then eventually the edge just tips a millimeter below the water surface and suddenly just fills
now
in.
Now that bucket is underwater.
Yep.
This event is called the Zanclean Flood. Again, the Zanclean is the time period, the first age of the Pliocene, starting at 5.33 million years ago. Hypotheses have varied. This has been actually, from what I've read, quite a big debate over what was this like. Was it a gradual refilling? Was it multi-phase? Or was it a single spillover event? I have seen some papers that fell fairly strongly on one side or the other. There was a paper that I came across that was very strongly arguing against the idea of a single event, that was suggesting, well, the evidence shows that it might have been more gradual. Some research has pointed to potential evidence of rising sea level and marine water conditions before the actual official end of the salinity crisis, but most of the, at least recent papers that I've seen, seem to support the opposite event, that it was a single refilling event.
Interesting.
A flood.
Yeah.
That the tectonic situation, the sea level situation, and possibly the erosion of that intermediate barrier happened relatively quickly, leading to a massive overflow into the Mediterranean, which, again, was hundreds of meters below sea level.
That's scary.
Just you wait.
That's intimidating.
The evidence that is pointed to for this includes a major erosion channel. So just this gouge in the sediment at the bottom of the Mediterranean that I saw reported as about 400 kilometers long and hundreds of meters deep in the western part of the Mediterranean. There's also a massive pile of sediment around that area that seems to be a deposition of sediment from that floodwater. Like, it came in and then it dropped its sediment. That pile is 160 meters thick and 35 kilometers long. It's a giant bar at the end of that flood flow. The stratigraphy of the area, according to some researchers, seems to indicate one major flooding event. Wow. Now, I'm going to introduce you to a new vocabulary word. At least it was new for me. You might already know this word. The word is sverdrup.
No.
A sverdrup is a unit of measurement of volumetric flow rate.
Oh, no.
It is usually used for ocean currents. I bring this up because research has estimated what the flow rate would have been during this refilling of the Mediterranean, during the Zanclean flood.
I don't like that you had to introduce a new term to explain this.
Yeah, and you're about to see why. Models predict peak discharge of around 100 sverdrups. Let's explain what a sverdrup is. A sverdrup is named after a person, a scientist, I suppose, is 1 million cubic meters per second.
Whoa.
That is roughly 264,000 US gallons per second.
Ooh.
As I said, usually this is used for ocean currents.
Yes.
Like, that's what this is meant to be measuring.
Giant flows.
Yes. How much in this kilometer by kilometer section of ocean, how much water is moving through here.
Yes.
1 sverdrup, 1 million cubic meters of water per second. For comparison, the Amazon River flows at 0.2 sverdrups. One reference, I think this was on Wikipedia, said the entire global input of fresh water from rivers to the ocean is estimated to be approximately 1.2 sverdrups.
That's not as high as I was hoping you would say.
Which, incidentally, means that the Amazon River, I guess, is like a sixth of that, which is not surprising.
Yeah, no. The Amazon gets bigger every time I learn about it. It's so big.
The Antarctic Circumpolar Current, which is the world's largest ocean current, moves at around 125 sverdrups.
Okay. I was going to say, if you were about to say like 10,
No.
I was going to have to leave the room.
This is one that I looked up just for Will. Will, when you were at the Florida Aquarium, do you recall how big your biggest enclosure was?
Oh, yeah, we were...
The coral reef?
500,000 gallons.
500,000 gallons. 1 sverdrup is 530 times that per second.
Woo!
Peak water discharge in the Zanclean flood event is estimated. I've seen estimates of tens of sverdrups. The peak that I saw reported in a couple of papers was 100 sverdrups.
That's
the Amazon River times 500.
one, and this really puts, because like many of us have seen at least video, and some may have experienced. Which, if you have, I am so sorry.
Sorry for bringing it up.
The intensity that a flood can have. That flood water, when a large volume of water moves through a restricted space, the solidity of ground becomes an illusion.
Yeah.
It shows you how actually unstable ground actually is, as it just tears the riverbank away. There's videos of like bridges just slowly eaten by water.
There were videos of that from this area when Helene came through.
And that's like, those are normal flash floods feels, but like that is not.
Like, that's like a yearly or decadely event.
Those happen multiple times within a person's lifetime around the world at one place or another. That is a fairly common occurrence on Earth. Thinking of that kind of flood and force on this scale is the only global event I can think of that intimidates me that much is when we're hit by space rocks.
Yes.
Like, that's terrifying.
I did a little bit of math to really drive it home, because not everybody knows how big the Florida Aquarium's coral reef is, and also 530 times 500,000 gallons doesn't mean anything.
Yes, that's sure, bajillion.
How many Olympic swimming pools is it? An Olympic swimming pool is 660,000 gallons. Typically, I did look it up just in case, and it turned out that the math is harder. I picked a lake, a famous lake, Loch Ness. Loch Ness is a impressive, famous lake in Scotland. It is among the largest lakes in Scotland. It is 37 kilometers long, or 23 miles long. It has a total area of 56 square kilometers, or 22 square miles. It reaches depths of over 200 meters at its deepest. It is not the biggest lake in the world, but it is a sizable lake.
Yes.
It would take you a good chunk of time to motorboat from one end to the other. It'd take you an hour, I guess. I don't know how fast a speedboat goes.
Yeah.
But if you're going 20 miles an hour, it's going to take you an hour to go from one end to the other.
Yes.
The total water volume in Loch Ness, according to Wikipedia, is 7.5 cubic kilometers, or 1.8 cubic miles.
Whoa.
According to my calculations, a flow of 100 sverdrups, as estimated for the peak flow of the Zanclean flood, would completely fill the basin of Loch Ness in 75 seconds.
Yeah, like this is
it's so much water.
day after tomorrow kind of vibes.
Yes, yeah, this is the wave coming down
Yes.
the streets of Manhattan.
Exactly. Like, that's how terrifying this would be to just witness this, not even be in its path.
Yeah,
to watch this.
just to know about
Yeah,
it.
to be on a mountain watching this come
Can
across
you
the
imagine
landscape.
the noise?
Yeah.
Just for
Like,
miles.
surely you would have to be able to feel that.
Yeah.
Like, through the ground. That's horrifying. Oh my gosh, I love it.
It is predicted that the Mediterranean mostly fully refilled in a few months to a few years,
Ugh.
with implied sea level rise of as much as 10 meters per day.
Whoa.
That's at high tide, and then right when high tide comes back around, the sea is 30 feet higher than it was before.
Yeah.
Now, again, there has been some back and forth
Yes.
on how abrupt was this, how quick did it happen, but it does appear that the Mediterranean Sea refill was some level of highly dramatic, possibly catastrophic event.
Whoa.
Absolutely preposterous.
Earth, what are you doing?
What a place. Now, we talked a little bit about the local after effects of this event, right? Because on the surface, right, from above, flying over in a helicopter, looking down, I imagine that if you came to visit in the middle of the salinity crisis and then 100,000 years afterwards, it would look basically the same.
Mm-hmm.
It's the water was gone, now it's back.
Yes.
Right, not the same, but all that has changed is the water's back.
No, we had a pool, we dried it out during winter, and then we
Yes.
refilled it come next summer.
But in addition to the evolutionary mix-ups in the area, there are some other long-lasting impacts that this had. I'm going to say a pair of words here because I want that some people out there will know what these terms mean right off the bat, and I want them to have the same experience that I had when I first read these words. Isostatic rebound. Isostatic rebound is a term that is typically discussed in relation to ice sheets.
Yes.
During, for example, the late Pleistocene, when you had these giant ice sheets that formed on top of the continents, that much weight on the land actually pushes the land surface down.
Yes.
So after they melted, the land rises back up. This is actually still happening in some parts of the northern parts of North America, where the land level is rising slowly back up because 20,000 years ago, there was 2 miles of ice on top of it.
It's like when you crush a foam thing, like a foam bedspread, and it just slowly has to refill with air.
It's that, but the Earth.
Yep.
Because, the crust is malleable.
Yes.
It's very slowly malleable.
To us, it's solid, but over thousands and millions of years, it's not.
And you can see evidence of that rebound in faulting and changes in the geologic record. You get cracks and deformations and stuff.
Yes.
During the Messinian salinity crisis, lots of water was gone.
Yeah.
Plus, lots of erosion was happening. So it is predicted that the Mediterranean lost a lot of weight.
Yeah.
And there is some evidence, it sounds like limited evidence at this point, but some evidence of geologic deformation that suggests during the Messinian salinity crisis, the land rose up a little bit because however much, I don't remember what the number, however much bajillions of cubic kilometers of water weighs, which is a lot.
Oh yeah, water's so heavy.
Water is heavy. That was gone.
Ugh, that makes a lot of sense. I know a similar thing can happen with swimming pools, where if you drain a swimming pool in areas with high groundwater, the pool can effectively become a boat and get pushed up by the now denser soil around it.
Yeah.
And that's how a lot of times the drained pools end up being non-usable, because that shifting cracks the pool. And when you try to refill it, it just drains out now because fractures have formed in a very similar way.
The Messinian salinity crisis is also potentially expected to have some effect on world oceans. According to some papers that I read, this event saw the deposition of approximately 4% of the world ocean's salt.
Oh, yeah.
Because that's
there.
1 million cubic kilometers of salt is just out.
Yeah.
Out of the ocean in this place. This could potentially have wide-ranging consequences. It sounds like there hasn't been as much research into this question yet, but some papers have pointed out that gypsum especially is calcium sulfate, which means that as gypsum's getting deposited, calcium is being removed from the water.
Which is important.
Which is important for calcium carbonate, which is not only a big resource for organisms that are building their shells or skeletons out of it, but also calcium carbonate is an important part of the carbon cycle.
Yes.
So if the calcium carbonate cycle is disrupted, that can mean less carbon availability, which can, because the ocean and the atmosphere interact with each other, which could potentially have led to decreasing carbon dioxide in the atmosphere, which can cause cooling on the planet. And then the return to more normal salt levels over time could have reversed that. Not to mention the impacts of whatever that did to the ocean currents in the Atlantic near the Mediterranean. Were there organisms that now spread out of the Mediterranean?
Yes.
This, chemically and biologically, would have done something to the world oceans. Obviously not something super dramatic, because
not nearly as
we haven't noticed it.
Crazy as what happened in the Mediterranean.
But there is the potential for more clues to be found for how this affected the world.
Yes, which makes complete, while the Mediterranean is still minuscule compared to the global seawater supply, you can't just shut off a whole, room of a building and it not affect the way the space is now utilized, even if it's just as simple as once again using a building, the airflow within the building.
Yes.
So if you shut all the doors and vents to a room, the air now flows differently. Currents are going to have to adjust to this new setup.
Another wide-ranging tie-in to the Messinian salinity crisis is the study and understanding of salt giants.
Yeah.
As I mentioned, salt giants are known from all across Earth history, all over the world. The Messinian salinity crisis is a very well understood example of a salt giant, which means it's a good case study for understanding why they happen, what causes them to happen, and what effects they have afterwards. Also, some research has found a potential link between salt giants and mass extinctions. Notably, the Triassic mass extinction, episode 15, volcanic activity is known to have led to ocean anoxia. There are salt giants that formed just before this that are thought to have exacerbated those conditions in the water.
Yeah.
Salt giants might have made this worse, the drying up of some areas. There have also been some papers that have pointed at potential links with salt giants around the Permian mass extinction.
Okay.
Episode 45. So salt giants might also be a component of some mass extinction events.
Which makes sense. That is a dramatic thing, and we just listed tons of reasons why it can be devastating to environments.
And it seems unlikely that this sort of evaporation event, these salt giant formations, would be single-handedly responsible for a true mass extinction, but they can certainly make things worse.
Yes.
They can certainly make it harder. And in fact, some scientists have pointed out the late Miocene around the world does see gradual declines in certain groups like mollusks and marine mammals, which is thought to be related to cooling temperatures. That this is at a time when the Earth is just gradually getting cooler. This trend almost certainly is not caused by the Messinian salinity crisis. These are two different things. But it is possible that the Messinian salinity crisis made it harder for life to be resilient or to recover from those changes. That if there's something else already going on the planet, having a whole chunk of the Earth, especially in a very diverse region like the Mediterranean, might mean that your net losses are going to be lower or your recovery is going to be slower.
No, it's the equivalent of the fact that your car broke down isn't why you're having a particularly hard time, but the fact that your car broke down at the same time that you got a new job or got sick or had something else happen combines to make it a really bad month.
Also, there is the prospect of the future. And I only bring this up to mention one thing that I saw in one paper. This was a very recent paper looking at the geology of the region and sort of the tectonic activity that caused and then ended this event, that noted that tectonic activity that caused and ended the event is ongoing in the region.
Yes.
So, as they mentioned, it's possible that the salt giant formation of the Messinian salinity crisis is merely an early phase of an ongoing series, that there may be more salt giants to come as the Mediterranean basin continues to be surrounded by continents on all sides.
Yes, we could just be in an interim of the formation of these giants and a reprieve period from this process.
So perhaps that is the first salinity crisis of the Mediterranean Sea.
Yeah. Man, that's so intense. It's so intense on so many different fronts. Like, the amount of water loss is staggering. The deposits that left behind are... I am always floored by the size of deposits when it's just like, yeah, here's the deposit. And when you think of a layer of earth, in my brain, I still think of layers,
Yeah, like a thin section. Maybe it's a couple of feet,
Like it's, layers on a cake. It can be thick, but it's a layer. But there's no, this thing's like almost a mile thick.
Yeah. There is a picture that I will put in the blog that is 100-meter high cliff of gypsum.
Yeah.
That I think is in Italy.
And it's just like, here, layer.
Yep. Well, because this is hundreds of thousands of years of continuous or repeated salt deposition.
And then the idea of it filling back up in one event. Just staggering in so many different ways.
Just the world's best water slide for a little bit.
Right?
There was a crab, right? Who was just right there when the first, just that little trickle of water is like, oh, what's happening here? Oh, there's water coming through.
It's the front door and Jumanji.
Yes.
Of the house is the one little. Yep. Oh man, it's the Mediterranean was already a very cool, interesting place. Lots of cool animal life and ecosystems. Lots of cool human history, like tons of epic human events have happened around the Mediterranean.
Yeah. The Mediterranean is one of the first places that we learned to be on the ocean.
Yes, exactly.
Like boats. That's one of the first places that humans did boats.
Yeah, like awesome, amazing place. Then there's this drama that precedes so much of what we think of.
Yeah.
That's just
Interestingly,
crazy.
so this is way before humans. Like, Homo sapiens are not around. Although this is at a time where like early Australopithecines were hanging out in Africa.
Yes.
So it's very possible that some of our distant ants, like Australopithecines, not Lucy, this is a little bit before Lucy, that they heard it.
Yeah.
They were hanging out on the savannah or whatever, and then there was just this the sound of a distant waterfall for 3 years.
Yep.
That was just part of the background noise.
Yep.
I wonder if it made it harder for like elephants to communicate with each other.
Right?
Was this like noise pollution?
Yeah.
In the nearby land and ocean, where whales for a few years like, no, you just can't go near there because I can't hear what you're saying if we're too close to the Mediterranean.
And I wonder if you would hit a point where like it had widened stuff and hit where it's still flowing with a preposterous amount of power and energy, but it's happening over such a large area now that an individual can't really witness it unless you're measuring it.
Yeah.
Like, I'm sure it hit a point to where it feels like, okay, yeah, it's just normal flow now. But when you zoom out and actually take the measurements, it's like, no, it's still really not.
Right. This is a few hundred Amazon rivers worth of flow into this space.
I also wonder if it would be one of those where it's like, at the surface it looks normal, but if you dive down...
If you're on the seafloor.
The speed picks, because like that'll happen with tides, where at the surface you won't really notice, but if you get just deep enough, you'll hit currents that are flowing against the sea, the shoreline or the shore floor, and because water has to flow differently when it's flowing around and over stuff, that can speed it up. So I wouldn't be surprised if it hit a point where the surface, like, it quiets down, you don't really notice it, it looks like a normal river now, but if you dove down, you would be killed.
Yes, they just zoom.
You would be dragged into the depths of the Mediterranean within minutes.
Deposited in that giant 16-kilometer thing of sediment.
Just, there's a term for those riptides.
Yeah, it's
just
like a riptide.
The most aggressive riptide in history.
So the Messinian salinity crisis, super dramatic event, fascinating, still being actively investigated. This is an event that we only really recognized truly about 50 years ago. So this is still under active investigation. There are still things that are debated about the nature of this event. It is entirely possible that, 10 years after this episode comes out, there will be a bunch of updates that the things that we would have to add if we did the episode again.
Yes, exactly.
To say, actually, this is what we used to think, but now we know that it was 3 flooding events or something like that.
Yes.
Alas, I leave all of our listeners with this to think about while you go to sleep tonight. Enjoy the thought. I hope that there aren't people who are like, afraid of water.
Yes.
This is a bad episode to listen to if you're afraid of the water.
Someone's listening to this on their AirPods while they're kayaking down a river.
Just when you thought it was safe to go back to the podcast. Hey, before we wrap up this episode, there is another thing to do, and that is a patron question. We so much appreciate the support that we get from each and every one of our patrons. There's all sorts of goodies you can get supporting us on Patreon, one of which is the ability to ask questions that we will answer here on the podcast. Will, would you do the honors?
Happily. Our question is from Corbin, who notes that in episode 202, we mentioned that the fungi farmed by fungus farming insects are often only known from those gardens. Knowing that farming ants and termites likely had one origin each, do we know if the same has happened with the fungi themselves? Does each ant or termite species farm exactly one fungus species that evolved in parallel with them?
This is an excellent question. This is a follow-up to our fungus extravaganza just a couple episodes ago. So, yes, in that episode we discussed the fact that fungus farming ants and fungus farming termites are related groups within ants and termites. So termites seem to have evolved fungus farming one time, and there is one group of ants that does fungus farming.
Yes.
So this is a limited evolutionary history. I went searching and found some papers that had the answers to these questions about whether the fungi are all related.
Convenient.
In termites, all of the fungal cultivars, that is, the fungi that they farm, are all within the genus Termitomyces descended from a single ancestral domestication event.
Yeah.
So, yes, termites domesticated fungi once, and all fungus farming termites and all of their farmed fungi are descended from that original ancestral event.
Which that's got that feeling of like our ancestors. Like we have carried this tradition through the ages.
Yeah.
That is very cool.
That being said, not every termite species is specific to the fungus that they garden. Within this group of fungi, there are several subgroups. Same with the termites. There are clades within the overall family tree. And each group has a group. So this group of termites farms this group of fungi, but within that subgroup, the fungi are often swapped and switched between different lineages.
Gotcha.
So not across the whole farming termite family tree, but if you're in like section A of that tree, those lineages of termites can exchange fungi from different cultivars.
Gotcha.
So not every species has their own specific fungus, but groups of species have specific groups of related fungi.
Yeah.
So termite farmers are either specifically adapted to cultivate certain types of fungi, or certain fungi are suitable for certain termites.
Cool.
Ants are different. In ants, we see multiple lineages of domesticated fungi, which suggests that the domestication of fungi happened 2 main times with some other outliers. So a few different groups of fungi have been domesticated within this group of farming ants. A single ant nest typically has only one type of fungus that they're guarding. But the same ant species can have different fungi in different nests.
Oh.
So like I don't know if leaf cutters work this way, but like those leaf cutters over there are farming that type of fungus. This colony of leaf cutters, even though it's the same species, might have a different fungus that they're actually farming.
Huh.
In fact, apparently most farming ant species are known to cultivate at least 2 different fungal lineages. And the fungi aren't always closely related to each other.
Oh.
You can have the same ant species or very closely related ant species farming fungi from multiple distantly related groups of fungi, and you can have closely related fungi that are farmed by distantly related farming ants. So to answer Corbin's question, it's complicated.
Yes.
Termites appear to have domesticated fungi 1 time. Ants seem to have done it a few times. Neither group is species specific to, like, this species only farms this species of fungi, typically. Termites are close to that. A group of related species only farms a group of related fungi species. Ants do whatever they want.
Yep.
And I didn't find a lot of detail about fungus farming beetles, but it seems that they are similar to ants.
Yeah.
Which makes sense because fungus farming itself evolved in beetles like 7 different times.
Yes, so it would be very surprising if they all used the same fungi.
Yes, that would be very strange.
Like that I would have so many questions about what's up with that fungi.
Yep.
If it's the one that happened every time. That's very cool. And it's one of those scenarios that feel both options are weird in different ways. Like domesticating fungi once and then everyone diversifying from those ancestors is pretty intense.
Yeah. And clearly it works because there are thousands of species of fungus farming termites.
Yes. So like super successful. Crazy that it was that even from a single origin, it was that crazy successful.
Yes.
And then on the ant side, that's a level of flexibility that seems surprising for such a, at least to our typical thinking of insects, specialized, high-level, complex behavior.
Well, and also because there aren't that many fungus farming ants. I want to say it's like 200 fungus farming species. The numbers are in episode 202. I don't remember them off the top of my head. I was expecting the opposite.
Yeah.
Like termites, who are so diverse in their fungus farming, might have a bunch of lineages. But no, termites did it once and did it great. And ants have been sampling different groups of fungi and trading them between each other for millions of years.
Well, a single species having multiple fungi that individual colonies might be cultivating, that's crazy to me. Like,
Yeah.
that makes me want to know, is this a way to like avoid competition? Is this because you live in different parts of the forest?
Sure. Do you get the same benefits from the fungus? Like,
yeah.
Is that nest farming a fungus that is extra high in nutrition and this nest is just missing out?
Yeah. Or is it just a luck of the draw of like, hey, listen, your queen came from a colony that cultivated this fungus.
Yep.
And her queen...
It was a dry year. This is the one they got.
That queen before them came from one with that same You have the fungus you have because it's the lineage that you came from.
Yep.
We don't get the fungi from the environment. We pass it down to colonies. So it's just happenstance.
Although it does also sound like they can swap fungi.
Yeah.
From time to time. So super cool. Fungus farming could be its own entire episode. So it's a fascinating topic.
That's amazing.
Corbin, thank you so much for asking that question. Thank you to all of our patrons for all of their support. Listeners, there will be a blog post after this episode on our website. You can find the link down in the episode description for photos of things and links to more resources and descriptions and stuff. It's November, which means spooky season is officially over. Mm. If you missed out on it, go back and listen to those episodes. And if you missed our spooky live stream, it is archived on our YouTube channel, so you can go check that out.
The spooky Discord channel is always open, so you can still share your thoughts. I want everyone to know you can share your thought for any episode at any time of the year.
Spooky, the Discord server does not work like the Croc and Snake Discord servers. That is a 24/7, 365 Discord server.
Always welcome.
There's also a separate Speculative Evolution Discord server.
Yes.
So there's tons of fun discussions. There's also an art server, an art channel on there, I should say. So there's all sorts of different ways to get in on this sort of stuff.
Yes.
It's November, which means the Q&A, end of the year Q&A form is officially open. Every year we end off the year by doing a massive mailbag episode where we just answer as many questions as our listeners want to send in and we can answer before we have to go to sleep on whatever day it is that we record it. Find the link through the links in the episode description of this episode or on our website. Go to the Q&A form. Go ahead and submit one question, please, that you would like to hear us answer. This can be a question about paleontology. It could be a question about us. Some of our listeners like to send in nonsense questions, and those are pretty fun, too.
Yeah.
Please go ahead and submit those. That form will be closing at the beginning of December, so don't wait too long. A huge thanks to all of the people who requested this episode. A huge thanks to all of our patrons who support us and allow us to do all the things that we do. You can find a link to our Patreon in the episode description. And an extra special giant thanks to our top tier patrons, Sarah May, Robert Mart, Melissa Barksdale, and Danielle the Bug Lover. Thank you so much for your incredible support of our podcast. And thank you, you, who's sitting right there in your car, I can see you, for listening to the podcast. Thanks for sticking with us through this discussion of a just truly fascinating... I put off this one for a little while because I was like, I know this is a cool event, but I don't actually know very much about this event.
Yeah.
And I'm not sure how well it's going to fit into an episode format or how much information I'm going to get. And then I found a couple of just perfect references that were really helpful. And this was super fun.
Yeah. No, I learned this was one of those where I was familiar with a lot of the concepts, but I was not actually at all familiar with this event. Mm-hmm. So this was all new information for the most part.
Yeah.
And it's humbling.
So for any of our South European or Northern African or Western Middle Eastern listeners, go out and give a little wave to the Mediterranean Sea for us and say that you're sorry for what it had to go through.
Yeah, just gaze upon it, and then picture it all filling up within a couple of years.
It's been through some stuff. Be nice to it. Watch out for great white sharks. Apparently they're in there now. We release episodes every fortnight, which means that there will be another episode in 2 weeks. Oh, that's episode 205, which means Allie's coming back for plants. Which we'll have to ask Allie about plants in the Mediterranean. I bet that there's a lot of cool plants in that climate region.
Absolutely.
That are super cool. Listeners, if you have a favorite Mediterranean plant, let us know. Anyway, come back for that. We'll be talking with Allie about plants and stuff. And other than that, bye.
Bye.
Thanks for listening to the Common Descent Podcast. You can follow us on Facebook, Twitter, YouTube, and check our WordPress blog for pictures and links after each episode. Huge thanks to our patrons whose support helps keep this podcast running and who get access to bonus goodies on Patreon. The song you're hearing is called On the Origin of Species by Protodome, which we found at ocremix.org. Thanks again for listening. We hope you'll join us next time.